Ladies and gentlemen, I have tricked you all. I know when you clicked on this video, you read the title and you thought that this talk is going to be about whitebox streaming algorithms for approximating the length of the LIS. LIS stands for the longest increasing subsequence. So it's given a sequence, you have to find a subsequence, a, a subset of elements in the sequence that are in increasing order. And the longest such sequence is the LIS. And you probably thought, yeah, this is about streaming algorithms that approximate the length of the LIS. But that's not what this talk is about. I will talk about whitebox streaming algorithms, but for most of the talk, I will focus only on the very simple equality problem. There's a string X, there's a string Y, and the goal of the algorithm is to determine if X is equal to Y. This is what most of the talk will be about, and only at the very last slide will I cover the main result about LIS length, and that's where I'll also discuss the prior work. So if you want to jump to the discussion about LIS length, where I talk about the result in the paper, then just move ahead in the video. The very last slide is about that. Most of the talk will be about whitebox streaming algorithms for equality, and that's where I want to get started. So let us start. I want to first define the whitebox streaming model. And before I do that, let us recall what is the standard streaming model, the traditional streaming model of computation. The streaming model of computation is a model of computation designed for inputs that are too large to fit in memory. So suppose your input is written on a tape. This string is your input. And this tape is so large that it cannot fit in the memory of your laptop. The only way the laptop has access to it is it can go over the cells in the tape in order, and it can process them one by one. Okay, so it has this tape. It starts from the beginning of the tape at this point that says 2. It reads 2. It does some processing. It maybe changes its state, maybe it changes its memory in some way. It does some processing. And then it moves to the next cell. Now that it has moved on from 2, it no longer has access to the cell that has 2. It cannot read it anymore. All it has is its memory, and now it's on the cell that has 1. So it will read this 1. It will again make some changes. It will do some processing, update its memory, and then go ahead. Okay. So this is how the algorithm will proceed. It has a very long input, 2 bit to be stored in memory. It will go through this input in one pass from left to right. It will read all the entries one by one. At each step, it will do some processing and then move on. And once it has moved on, it will forget everything about the tape that had so far. All it has is its memory, and everything that happened is now forgotten. Just the memory is with it. Okay. So the goal is to given such an input and a function, the function could be the equality function or the LIS function or many functions. Maybe you want to know which is the number that appears most often on this tape. The goal is to given this tape and a function, can you compute the function using as little memory as possible? Recall the memory is the amount of information that the algorithm carries from one cell of the tape to the other. So more memory gives the algorithm more power. It can recall more things. Maybe it stores some of the entries it saw so far. Maybe it does some processing and stores them in some process form. It gives it more power. And you want to know what is the smallest amount of memory that is needed to compute a given function. This is the streaming model. It can be deterministic. It can also be randomized. So maybe your algorithm also has some random points, and it can use it to compute the function in a more efficient way. And the smallest amount of memory required for a function is the streaming space complexity, which will be the main object of interest for us. Okay, now let us move to the whitebox streaming model. Now, this diagram, this is an adversary for me. Wherever this diagram is, that slide is talking about the whitebox model. So here I'm talking about the whitebox streaming model, which is somewhere in between a deterministic streaming algorithm and a randomized streaming algorithm. So a deterministic streaming algorithm is one where the algorithm has no randomness. Okay, it is a deterministic. Every step, you know what is going to happen next. A randomized streaming algorithm is one that has randomness. If there is a worst case input and the algorithm is allowed to toss random points. A whitebox streaming algorithm lies somewhere in the middle. It is more powerful than deterministic, but less powerful than randomized. And the way it is defined is that the algorithm is allowed to use random points. There are random points, but the adversary can change what happens later in the stream based on these random points. Okay, So what this means is the algorithm would start executing. It will read 2, it will read 1, it will read 0. It is tossing random points all along. And at every step, the adversary who knows the algorithm, who knows the code, and he also sees all the randomness that has been sampled so far, he uses all of this information to decide what is the symbol the algorithm is going to see next. Okay, so at this point, it was at 3, it had some state, it had some random points. This adversary knew all of that, and based on that, it decided the next input, which happened to be 4. And obviously, the adversary will do it in a worst case. So he wants the algorithm to fail. So he has all of this information. The algorithm will now maybe toss some more coins. Maybe there are some fresh random coins, and it processes 4, updates its state again. And the adversary again makes a decision as to what the algorithm sees next, which maybe is this number 2. Okay. So this is the whiteboard streaming model. You can imagine the input tape as being blank in the beginning, and at every step, the adversary generates the next input the algorithm sees. The algorithm can process this input, it can toss random points, which will all be visible to the adversary, who will then generate the next input, and so on. Okay. This is the whiteboard streaming model. And like I said, it is somewhere in between deterministic and randomized streaming algorithms. It is more powerful than deterministic streaming. It is less powerful, or at most as powerful as randomized streaming. And the way to see that is, well, one direction is obvious. If you have a randomized streaming algorithm, then there's a fixed input and then there's a random point. So that's like saying the adversary cannot change the input based on the random point. So it's obviously more powerful. The adversary cannot control the tape. So whiteboards being weaker than randomized is very easy to see. It's also easy to see that it's at least as much as powerful as deterministic algorithms, because the deterministic algorithm, it does not have any randomness. So the adversary does not need to wait for the algorithm to toss random coins to decide what is going to be the next input. It can just decide it in advance. It can just say, oh, if I give 2 in the first cell, then the algorithm will do that, which is a fixed function because the algorithm is deterministic. Then I'll want to give 1, then I'll want to give 0, and so on and so on. But it can do all of that at the beginning itself. So at the beginning, it can come up with this worst possible input. It does not need to do that on the fly. So there, the power of the adversary is just picking the worst case input, which is exactly what a deterministic protocol is designed for. Okay. So if you don't have randomness, you are deterministic and you are less powerful than whiteboards. If you have randomness, you're more powerful than whiteboards. Whiteboards lies somewhere in the middle. And this is the model that we'll be talking about in this paper. What is the power? Can we show lower bounds for the whiteboards streaming model? Now, like I said, this whiteboard streaming model, it lies in between deterministic and randomized. So if I want to show lower bounds for the whiteboards model, I want to first know, I should at least be able to show lower bounds for the deterministic model. And there is a very standard technique to show that. The technique uses the fact that in a streaming algorithm, all that the algorithm carries from one cell of the tape to the other is its memory. Once it has crossed this cell that had 3, the algorithm has forgotten all of this 2, 1, 0, 3, whatever it read. It does not have access to it anymore. It will never have access to it. It only has its memory state that it updated while reading these elements. And this is all that the algorithm carries to the next part of the tape, which is 2011. Okay, so you can use this to design a communication protocol out of the algorithm. What you can do is you can pretend that there is one party, Alice, who has the first part of the stream. This is some prefix 2103. This party, Alice, it can run the algorithm on this part of the stream. It can go cell by cell. It can do the processing, whatever the algorithm does. And then whatever the memory it gets after processing these 4 entries is the message it sends to another party, Bob, who has the rest of the stream. Okay, so it runs the streaming algorithm cell by cell. Eventually, it runs out of the tape. It has a memory state. It sends it to Bob. Then Bob has this memory state. It starts running the algorithm again cell by cell on this suffix. Eventually, it will exhaust the whole stream, and then Bob can output. Okay, so whenever there is a streaming algorithm, there is a communication protocol for the same problem, where the size of the memory of the streaming algorithm is the length of the message in the communication protocol. Okay, so a streaming algorithm implies a communication protocol. flip it around, you get that a communication protocol lower bound, so a lower bound on the message length of a communication protocol would give a lower bound on the memory of a streaming algorithm. This is a very standard technique to show streaming lower bounds. It works for deterministic communication protocols, which imply lower bounds for deterministic streaming algorithms. It works for randomized communication protocols, which imply lower bounds for randomized streaming algorithms. And probably the most classic, the first lower bound that anybody who studies communication complexity sees is the lower bound on equality. So Alice has a string X. Let's say it has n bits or n numbers, n equal to 4. And Bob has again a vector y with n equals to 4 numbers, and they want to check if x is equal to y. And this is the equality problem. Alice has x, Bob has y. They want to check if x is equal to y. And the very simple lower bound on communication, a very standard result says that if you want to check this deterministically, then you need omega n bits of communication. So the length of this message needs to be omega n, where n is the length of the inputs. Okay, I emphasize this for deterministic protocols. You can do it much more efficiently if you have randomness. But for deterministic protocol, this lower bound holds. And therefore, for deterministic protocols for equality, you need omega n bits, which means for deterministic streaming algorithms for equality, you also need omega n bits of memory. Okay, so this is about an approach to prove streaming lower bounds via communication. You transform the stream into a communication task where Alice has one part of the stream, Bob has the rest of the stream. There's a message that is sent over. The message corresponds to the memory. So if you lower bound the communication, you lower bound the memory. It works for deterministic, it works for randomized. And in fact, it also works for white box. So what you can do is you can define a white box communication model, which is very similar to the streaming model. And you can show that communication lower bounds for this white box communication model would imply communication lower bounds for the streaming, white box streaming model as well, memory lower bounds for the white box streaming model as well. So what is this white box communication model? It's very similar to the streaming model. So Alice starts with her input. She has some randomness. She can process this input. She can compute a message. And currently, Bob has no input. Then once she sends this message to Bob, then the adversary, who can see this message, you can see Alice's randomness, her input, everything. The adversary can compute whatever Alice knows, and all the randomness is visible to him. Then he decides what input Bob should have. So he sees this message, and then he decides, maybe now the worst possible input I can give Bob is 2011. So that's the one I'm going to give. Okay. So it's very similar. There's a part of the algorithm that is run. It has some randomness, but the adversary sees the randomness and then decides what input to give in the next part. It's very similar to white box streaming. And in fact, the implication of lower bounds on communication implying lower bounds for streaming still carries. And what you can show is that if you have a lower bound on the message length of a white box communication protocol, then that implies a lower bound on the memory of a white box streaming algorithm. Okay. In particular, if you want to show the lower bound on the memory needed for a white box algorithm to check if Alice's input X is Bob is equal to Y, then you can consider the same task in the communication setting and you can lower bound the message length. Okay. Okay, so this is what this slide has. It has the equality problem. Alice has a string X. It's a vector of numbers, 2103. Bob has a vector Y of the same length, let's say 2011. And they want to check if X is equal to Y. This is the equality problem. And what I'm going to show, the theorem I'm going to show in this talk, is that even in the white box communication model, this problem of equality requires omega n communication. So let us put this in perspective. There is a classic result that I mentioned that for deterministic protocols, this is omega n. There's also a very simple hash function based protocol. I can just sample a hash function and send the hash value to Bob. If you're allowed to use randomness, then that's very communication efficient. In fact, if you have public randomness, you can even make it constant communication. But the white box model lies somewhere in the middle. And we established that actually for equality, it is up to constant factors. It does not have more power than the deterministic model of communication. In other words, the white box communication complexity of equality is just like the deterministic case, which is omega n. Okay, so this is the result about equality that I'll talk about in detail. And the proof of this is essentially two steps. So I want to show a lower bound for equality. I want to show that without omega n communication, Alice and Bob cannot determine if x is equal to y. The first step of the proof will be to move from this general equality problem where Alice has x, Bob has y, and they want to check if x is equal to y, to a decision version. The decision version would be Alice would still have x, but Bob will have two values, y1 and y2, with the promise that exactly one of them is equal, the other one is not equal. Okay, so he just has to determine which one is equal. Is x equal to y1 or x equal to y2? So we will show that a protocol for equality implies a protocol for the decision version. It will be a very easy argument. And then the second step in the proof would be to actually prove a lower bound for the decision version. Okay. So this is the proof outline. Let us see what this decision version is formally. So like I said, instead of checking x is equal to y, Alice has the string x. This is an n-length string. Bob has two strings now, y1 and y2. And the promise is that x is equal to exactly one of these two strings. So in this case, x is equal to y2. It could also be equal to y1. And the goal of Alice and Bob is for Alice to send one message to Bob so that Bob can determine whether x is equal to y1 or x is equal to y2. Okay, so this is just a decision version. The output is one bit. Is it y1 or is it y2? It's just two possible outputs. And again, we are in the whiteboard setting. So first Alice will see her input. She'll toss some random coins. She'll send a message. And then the adversary will see this message and then decide what is y1, what is y2 for Bob. Okay. So this is the problem. It's called decide equality, or the decision version of equality. And it is easy to see that a lower bound for the decision version of equality implies a lower bound for equality. In fact, it's easier in the other ways, that an algorithm for equality implies an algorithm for the decision version of equality, because Bob can just ignore y2. He can just pretend y1 is the input and just run the algorithm for equality. If it says equal, then okay, fine, x is equal to y1, Bob has found out. And if it says not equal, then by the promise, Bob knows that y2 must be equal. So he just outputs y2. Okay, so an algorithm for equality implies an algorithm for decide equality. And put the other way, a lower bound for decide equality would imply a lower bound for equality, which is what we want. So how do I prove this lower bound for decide equality? Now, the key step in this proof, in many whiteboards proof, in fact, is to understand this power of this adversary. This is what separates the whiteboards from the deterministic and the randomized variants. In the deterministic variant, there is no randomness. In the randomized variant, there is randomness, but the input cannot change based on the randomness. What separates the whiteboards model is that, yes, there is randomness, but the input can change based on the randomness. So I mentioned this protocol about hash functions. That will not apply here, because Alice can, yes, sample some hash functions, send some hash values, but then the adversary sees this function, sees this value, and will give Bob some input that agrees on this hash. There are many such. It just needs to find some hash relation, so it will give it, and the protocol will fail. Okay, so things don't work because the adversary can change the input based on the randomness, and exactly the lower bound needs to capture exactly this. What is the strategy of the adversary? How does the adversary decide what is Bob's input? So what is the best thing we could hope for? Or as an adversary, what is the best thing we could hope for? How could we fail the task for Bob? Well, here is the best thing the adversary can hope for. The adversary sees Alice's input, sees her randomness, her message. Her message is denoted by M. And once it has all of this information, the best thing the adversary can hope for is to give Bob a pair of inputs, y1 and y2, such that we know exactly one of them has to be correct, such that the probability that y1 is correct and y2 is not is the same as condition on M, because Bob also sees the message M, is the same as the probability that y1 is incorrect and y2 is correct, again, condition on M. Okay, so if this is the case, then if this probability matches exactly, then Bob really has no clue. If he sees two inputs and both of them are equally likely to be correct, given the message M that he sees. And therefore, all he can do is guess one of them randomly, which would give him a probability of success around half. And that is the best we can offer. Okay, so this is what the adversary's dream is, to try to find some strategy such that Bob always gets a pair of inputs y1 and y2, such that the probability that y1 is incorrect is the same as the probability that y2 is incorrect. Now, what are the constraints? What should the adversary maintain? Of course, it can't generate numbers arbitrarily. The adversary needs to maintain that if you sum over all the y2, then the probability that y1 is right, y1 is correct, and y2 is wrong should exactly be the probability that Alice's input is y1. Okay, so Alice has some input x, and y1 should have that input. Only then y1 would be right. If you sum over all y2, then this event, it goes away. So it's just the probability of y1 being right, which is just that the probability that Alice's input x is the value y1, given the message M. Okay, so this is the constraint. Note that this constraint is fixed by Alice's side of the protocol. The adversary has no say in this. Alice can decide how to compute this message based on her randomness, and whatever she does will fix this conditional probability. The adversary cannot stop this. These numbers should be anything. What the adversary can do is it can decide on these numbers. What is the probability that y1 is right and y2 is wrong? And the way I want to interpret these constraints is that you have a graph, and each vertex in the graph, it corresponds to one value of x. So it can be y1, it can be another value, it can be another value. For each such value, there is one vertex in the graph. And for each such vertex, I give it a weight, which is equal to this quantity, which is the desired quantity. What is the probability that Alice's input is y1, where y1 is this value given M? Okay, so I know M. Based on M, I can construct this graph where the y1, the different y1s are the inputs, the vertices, and the weight of these vertices is just the probability that Alice's input x is y1 conditioned on M. Now, what does this mean? Well, these talks about a pair of values, y1 and y2, and I want to read that as a pair, as a weight of an edge. Okay, so given y1 and y2, which are not equal, so it's a simple graph. This is a symmetric number because we want equality, so it's an undirected graph. And what I want is to assign weights to these edges. I want to compute these quantities such that the sum over all the edges from a given vertex equals the weight sitting on that vertex. Okay, so Alice decides by her message what is the weight on every vertex. And now the adversary has to come up with a graph, weights on the edges, such that for every vertex, the sum of the weights of the edges incident to it is the number sitting on it. Okay, so you're given a sequence of degrees. This is where the degree sequence comes in. These correspond to this. And you want to know if there is a graph, a weighted graph, a weighted undirected simple graph, such that for every vertex, the degree is exactly what is desired. Okay? So what we have shown just now is that if the adversary can construct such a graph, then he can fail the protocol. Then he will be able to generate y1 and y2 according to this requirement, which would mean that Bob will have no way to determine if y1 is correct or y2 is correct. And therefore, he can do nothing better than random guessing, which means he fails the task. So this, I shouldn't say equivalent, but we have reduced this problem from the adversary's perspective to construct a graph given a degree sequence. And now the question is, can we do that? Suppose we are given some arbitrary degree sequence, can we construct a graph where the vertex of the degree of every vertex matches its degree in the sequence? Well, in some cases you can, in some cases you can't. It's not true for all sequences, but there's a very simple condition that tells you when this is possible, when this is not. And let me just show you a couple of examples first. So suppose you have 5 vertices and the degrees that you desire are 4, 2, 7, 2, and 1. Then there is a graph that has this degrees, which is the graph in the picture. So here the vertex A has degree 4, the vertex B has degree 2, the vertex C has degree 4 plus 2 plus 1, which is 7, D has 2 and E is 1. So there is such a graph. So in this case, it is possible. But in this other case, where I change the degrees slightly, where the degrees are 4, 2, 9, 1, and 1, then I claim that there is no such graph. And the reason is that now the degree of C is too high. So no matter what you do, every edge contributes to both the vertices the same amount. So if there's 4, it's contributing 4 to A and 4 to C. So if the so if the weight you need for C is 9, then the sum of the weights for all of the vertices should be at least 9, because otherwise there's no way. Every edge would go to at least one other vertex, which would increase the weight there. So if the degree of C is more than the sum of all the other degrees, which is the case here, 9 is more than 4 plus 2 plus 1 plus 1, then there is no hope of constructing such a graph. Okay? And what we show is that, in fact, this is the only condition. The only way, the only reason you will not be able to construct a graph with a given degree sequence is when there is a vertex C in this case, whose desired degree is more than the sum of all other degrees. In other words, its desired degree is more than half of the sum of all the degrees. So as a fraction, it's more than half. Okay. This is the only where this is fails, and it's easy to, it's not hard. I mean, I shouldn't say it's easy, but it's not hard. You can have a greedy based procedure where you start with the vertex with the highest degree, then you connect it to an edge with the second highest degree. Typically, this is what you do. There's a third case when you have to look at the third highest degree, but it's a simple greedy procedure. You can implement it, and you can get a graph with any degree sequence as long as no vertex has more than half of the weight. Okay, so this is a result. It's talking about graphs and degree sequences. Let us put it back into the whiteboard's problem for decision version of equality. And there, the target weights were this. The target edge weights the adversary can decide is this. And this is possible as long as no vertex has more than half of the total weight. As these are probabilities, they add to 1. So this is possible as long as there is no y1 such that the probability that Alice's x is this value y1 given m is at least half. Okay, so if there is no such y1, then the adversary can always construct such a graph and fail the protocol. So if you were to have a correct protocol, then for every message, there should be one such y1. That's only way the protocol can work. Otherwise, the adversary will fail it. Now, in fact, if you have this property that for every message there is at least one such y1, then for every message there should be exactly one such y1, because again, these are probabilities, so add up to 1. So if you have two numbers that are more than half, that is impossible. Okay, so for every message you have at most one y1. So if it were to work, then you would need exponentially many messages, which would give you the lower bound. In fact, the lower bound is strong. Even if you want to have advantage that is exponentially small, then you would need this property for exponentially many y1, which would still imply an exponential number of messages or linear length of the protocol. Okay, so this is one part of the talk. What I have done so far is I have introduced the whiteboards model. I introduced the reduction from streaming algorithms to communication protocols. I said that communication lower bounds imply streaming lower bounds. And then we focused on this one problem of equality, where I showed a lower bound even in the whiteboard sense. I showed a communication lower bound, so it implies a streaming lower bound as well. And I showed that any whiteboard communication protocol needs omega in memory to decide this equality function. Even if it is only aiming for an exponentially small advantage, it needs omega in memory. In terms of streaming algorithms, it means that any whiteboard streaming algorithm that decides if x is equal to y, that solves the equality task, needs linear memory. Okay, now so much about equality. Now let me move to the actual problem in the paper title, which is approximating the length of the LIS. So the task here is very simple. You are given a stream, it has numbers as usual, and you want to identify the length of the longest increasing subsequence in this whole sequence. So interpret the tape as a sequence of numbers. You're allowed to remove some numbers of the sequence so that the resulting subsequence is increasing. And you want to know what is the longest increasing subsequence. You can construct this way. And what I'm going to do is I won't give you the whole proof, but I'll give you the idea of how to use this equality lower bound to get a lower bound on the LIS length, on even approximating the LIS length. And the idea is very simple, is you take your equality inputs and you offset all the entries by some suitable values. So here, all inputs were small. There are small numbers between 0 to 5. So let's pick something slightly larger. Let's say the number I want is 10. So what I will do is I will offset the first entry by 10. I will offset the second entry by 20. I'll offset the third entry by 30 and so on. So you had X and Y, you do this offsetting. Now this 2 becomes 12, this 1 becomes 21, this 0 becomes 30, this 3 becomes 43. Bob does the same thing. So for him, it's 2 becomes 12, 0 becomes, this should be 20, 0 becomes 20, 1 becomes 31, and so on. Okay. Now they do this offsetting. And now I claim that if X were equal to Y, then the LIS of this offsetted values of X prime and Y prime would just be N, which is the length of X. Okay. Why? Well, X is equal to Y. So these values are the same. Moreover, the offsets are the same. So even X prime is equal to Y prime, and they are increasing. So if you want an LIS, well, you can take some values of X prime, some prefix, and then you can take the remaining suffix of Y prime, or you can just take the suffix from X. Whatever you do, you cannot have more than N because it's just the same string repeated twice. Okay. So if X is equal to Y, then the LIS is N. And in fact, if there is a coordinate where Xi is less than Yi, then I claim that the LIS is now N plus 1. So here, for example, the third coordinate is 0 for X and 1 for Y. So Xi is less than Yi. And I claim that the LIS with offsets between X prime and Y prime is now N plus 1 or 5. Why? Well, Alice, she starts, her sequence is increasing. So she reads the first 3. Now she's at 30. Now the subsequence, it moves to this point, 31, which is larger than 30 because I know Xi is less than Yi and the offsets are the same. And then it reads the rest of the sequence for Bob. So this third coordinate is counted in both, which is why you get an extra 1, which is why you get this N plus 1. Okay. This is for a coordinate where Xi is smaller than Yi. It's actually without loss of generality because you can assume that it's not the case here, but you can assume that the sum of all the entries in X is equal to the sum of all the entries in Y. So whenever they are not equal, there would be at least one entry in X that is smaller than Y. And also at least one entry that is larger because the sum is the same. So whenever they are equal, my LIS will be N. Whenever they are not equal, my LIS will be N plus 1. So if I can solve LIS, if I can distinguish between the case LIS N to LIS N plus 1, then I can solve equality. Okay, so this tells me that the LIS for N bits, for distinguishing between N and N plus 1 should also have at least omega N memory. The only problem is that I don't want to show a lower bound for such a precise LIS value. I want to show a lower bound that holds even for approximation. So ideally, I want a constant factor, and that constant factor algorithm will not be able to discriminate between N and N plus 1. It will output the same in both cases. So it will actually not help the equality case. And the way we get around this is we use the fact that in our lower bound for decision equality, we were actually showing the lower bound against protocols that had an exponentially small advantage. So we can take many copies, and by it's a hybrid argument. You need to have some sort of hybrid argument to show that even if you have many copies, then you still can't distinguish between all the copies being equal or all the copies being not equal. And we can take these many copies to increase the gap. So what we do is instead of taking 1x and 1y for Alice and Bob, I take roughly, if the length is n, I take n many x's each has n coordinates, a total of n square length, x1, x2, xn for Alice, and y1, y2, yn for Bob. And now if all of them are equal, then we arrange them so that the LIS is still order n, or let's say n. And if the other case where all of them are not equal, then you get this +1 from every one of those n values. So, well, not a +1, but some plus some constant value for every one of those n values. So you get not n, but n times some constant. So maybe let's say 1.1. So if all of them are equal, then you get n. If all of them are not equal, you get 1.1n. And our exponentially small advantage ensures that you need omega n space to distinguish between these two values. But now an approximate LIS algorithm will also distinguish between these two values. So now we have shown that with this many copies trick, even an algorithm that approximates the LIS length can solve the equality problem, which needs omega n memory. The slight catch is now we blew up the stream length to be n squared because we had n inputs each of length n. So now the stream is n squared, which means in terms of the stream length, my lower bound is root n. Okay, so if you have an algorithm that approximates the LIS length with root n space, then that would violate my equality lower bound. So flip it around, I get that any algorithm that approximates the LIS length needs at least root n space. So this is the main result. If you have a streaming algorithm that approximates the length of the LIS, then that algorithm must have root n memory. And like I said, this is the last slide where I'll talk about the LIS. I'll cover the main result, which is this. Streaming algorithms need root n memory to approximate the LIS length. We show this for whiteboard's streaming algorithms. There is a prior work by Anna Dal and Parikshit Gopal in 2010 that showed this for deterministic algorithms. So our theorem can be viewed as extending their result from deterministic to a stronger notion of whiteboards. Of course, the strongest notion is the notion of randomized streaming algorithms, where this problem is still open, where we don't have any lower bounds, basically. For all we know, the length could be logarithmic even. So that is a great open question. There is some insight offered by this paper, Ramit Chakravarti, that I won't mention this talk, but I wanted the reference to be there. So this is the state of the art. There was a deterministic lower bound. We extended to whiteboards, and the randomized question is open. It's a great open question. And let me leave you with that. Thanks for listening.